Okay, so we continue our discussion of electrostatics, and I would like to consider a problem which will include two capacitors connected in parallel. Both capacitors are equal and have capacitance C, and the initial distance between the plates is d0, and here is also d0. In this problem, some positive charge is put on this upper plate, so we put here a positive charge plus Q. As the capacitors are identical, this charge will divide into two equal parts. So the upper plate here and the upper plate here will carry identical charges plus Q over 2. The problem says that the distance between the plates of the second capacitor is changed. We move the upper plate in such a way that the distance is reduced by half, so that the final distance will be the initial distance divided by 2. And the question is, what charge will go from one capacitor to another capacitor if the upper plate of the second capacitor is moved, if it's shifted downward? So this problem is on the laws of electrostatics, and in order to solve this problem we have to recall some electrostatics laws. The first and very important law is the law of conservation of electrical charge. If we put some electrical charge here on this upper conductor, then this electrical charge will be conserved, whatever happens. If we don't take this charge away and if we don't add more charges here, then the charge on the upper conductor will be conserved. It means that the charge on the first capacitor Q1 and the charge on the second capacitor Q2 will always, in the sum will always produce the initial total charge, will always produce the initial charge Q. So originally each conductor had a charge capital Q divided by 2. That was originally in the beginning of the process. But finally, when we started to move the upper plate of this capacitor down, the charges will change. Some amount of charge from one capacitor will flow to another capacitor, and we will learn why it happens. But the sum of the two charges will remain constant. The sum will remain the same as it was initially given to this circuit. Another thing which is important in this problem is that the two capacitors are connected in parallel. It means that the potential difference between these 2 points A and B is the same for both capacitors. This potential difference may change in time. The potential difference between these 2 points may be a function of time if we start moving this upper plate down. Then surely the voltage between points A and B will change. But this voltage at any moment of time will be the same for the first capacitor and for the second capacitor. And this voltage can be presented using the charge on a capacitor and its capacitance. So by definition, the voltage between the capacitor plates is the charge of the first capacitor, if we look at the first capacitor, divided by its capacitance. Also, the same voltage is applied to the second capacitor, and it will be equal, by definition of capacitance, the voltage is equal to the charge on the capacitor divided by capacitance. But in the process of motion of this upper plate, this second capacitance will be a function of time. The first capacitance does not change in time, but the charge of the first capacitor may change in time, and the charge on the second capacitor may change in time. And the capacitance of the second capacitor may be a function of time, certainly, because the geometrical dimensions are changing in time. We move the upper plate of the capacitor, the distance between the plates is changed, so the capacitance will change for the second capacitor. So we have such a relationship between the charges on each capacitor and the voltage between the plates of this capacitor and the corresponding capacitance. So the first capacitance should better be denoted as C1 and the second C2, because they are different. Initially they were the same. Initially they were equal. But in the process of changing the distance between the plates of the second capacitor, this will become different capacitance. So that will be C1 and that will be C2. And C1 remains constant in time while C2 is changing. So we have two equations with two unknown quantities, Q1 and Q2. And the capacitor is actually known. If we know the area of the plate and the distance between the plates, then we know the capacitance. We considered this issue last time, and we obtained this result, that the capacitance is the electrical constant times the area of the flat capacitor plates, the area of a single plate, divided by the distance between the plates. And as far as the first capacitor is concerned, this quantity remains constant because we don't change the geometrical dimensions of the first capacitor. The second capacitor can be expressed in a similar way. It will have the same area of the plates because originally the two capacitors were identical. They had equal dimensions. So the same area of capacitor plates for the second capacitor divided by distance, which now is a function of time because we move the upper plate. So here for the first capacitor the distance is constant. And for the second capacitor the distance is a function of time, and we know what function of time. Originally it was d0, and then it was diminished in time with some velocity. We assumed that we moved the upper plate with some velocity. Actually we have to move the upper plate and it will have some velocity. So the distance between the plates for the second capacitor will change according to this simple formula. Well, as we know the formulas for capacitance, we can obtain from the second equation here that, for example, Q1 will be equal to Q2 times C1 divided by C2. And C1 divided by C2 can easily be calculated now. So when we divide C1 by C2, the electric constant epsilon 0 will cancel, as well as the area of capacitor plates will cancel. And we will obtain C1 is inversely proportional to D0. It will be found in denominator, while C2 is inversely proportional to this expression. It will go to the nominator. So D0 minus Vt will be found in the nominator of this formula, in the nominator of this fraction. Now we know the relationship between the charge on the first capacitor and the charge on the second capacitor. And if we use this relationship in the first equation, then we can find these charges as functions of time. For example, if we take this expression for Q1 and substitute it here in this equation for Q1, we will obtain the following equation. So instead of Q1, I will use this expression. That will be Q2 D0 minus Vt divided by D0. And now I have to add another charge Q2. And this sum must be equal to Q, the original charge on the upper part of this scheme, of this circuit. From this equation, I can easily find the unknown quantity Q2. From this equation, Q2 may easily be found. It will be equal to capital Q divided by 1 plus D0 minus Vt divided by D0. Well, if we are interested in detailed behavior of this charge Q2 on the second capacitor, then we have all the possibility, because we know the time dependence of this quantity, so we know the time dependence of this quantity. But actually we don't need this detailed notion about how this quantity changes in time. The only thing we need is to calculate the final value for this charge. And the final value can be calculated because we know the final value for the distance between the plates of the second capacitor. And we know that the final value will be just equal to D0 over 2. So we have to substitute here D0 over 2 for the distance between the plates of the second capacitor. That value is the final value for this round brackets. And then what we'll find here, we will find that D0 divided by D0 will cancel, and the only thing remaining here will be 1 over 2, 1/2. So that will be equal to Q divided by 1 plus 1/2. That will be 3 divided by 2. That is the final value for the charge of the second capacitor after we have shifted the upper plate in such a way as to reduce this distance by half. After we have reduced the distance between the plates by half, the charge on the second capacitor will be equal to this value. Now we can easily find the charge on the first capacitor, as we have the relationship between these two charges. And the charge of the first capacitor can easily be found from here. For example, it will be Q, capital Q minus the charge of the second capacitor. It will be capital Q minus the charge of the second capacitor. So it will be capital Q minus 2/3 of Q. And that will be equal to Q divided by 3. So we know the final value of charges on both capacitors. The first capacitor will have a smaller charge. It will have the charge capital Q divided by 3. And the second capacitor will have a larger charge, twice this value, 2/3 of a Q. But in this problem we have to find what amount of charge was transferred from the first capacitor to the second capacitor. So the first capacitor lost some amount of charge. The first capacitor lost some amount of charge. And the original amount of Q1 was Q. It lost some unknown amount of charge, and finally it became Q divided by 3. From here, it's easy to find the amount of charge lost by the first capacitor. It will be Q minus the original charge of the first capacitor was not Q, it was Q divided by 2, certainly. Originally, the charge on the first capacitor was total charge divided by Q, and the same charge was on the second capacitor. So it was Q divided by 2 minus some unknown quantity, and that will finally give us Q divided by 3. So here we have Q divided by 2 minus Q divided by 3. So that is 1/2 minus 1/3. That will be Q divided by 6. Such amount of charge was lost by the first capacitor, and this amount of charge went by this rod, by this wire, and came to the second capacitor. So the charge on the second capacitor was increased by this amount, and we can easily see that the original charge Q plus Q divided by 2 plus this charge delta Q, which came from another capacitor. If delta Q is Q divided by 6, then 1/2 plus 1/6, 1/6 will certainly give us 2/3. That will certainly give us 2Q divided by 3 as a final charge. So this charge was lost by the first capacitor, and the same amount of charge was acquired by the second capacitor, because this charge went from the first capacitor to the second capacitor through this wire. Such is the solution of this problem, and the interesting thing in it, the interesting part of this problem, is the electric current which went through this wire. What is the electric current? That is a stream of electric charges flowing in the wire or in some other medium. The stream of electric charges is called an electric current. An electric current is usually denoted by character I, capital I, and it's measured in amperes. It's measured in amperes. One ampere, by definition, electrical current is amount of electricity transferred through the cross-section of the wire in a unit time. So as this is the definition, then we can write that electrical current is amount of charge divided by the time interval. Some electrical charge carried through the cross-section of the wire in a unit of time, in time interval delta t. So if delta t is 1 second, then electrical current will coincide with the amount of charge carried through the wire in 1 second, in a unit of time. So that according to this definition, according to this formula, the electric current is of 1 ampere is 1 coulomb divided by 1 second. That is, 1 ampere is such a current under which during each second the charge of 1 coulomb is carried through the cross-section of the wire. In metals, electrical current usually is carried out by electrons, but sometimes even in metals, the carriers of electric current are holes or positively charged particles in metals. Also, in semiconductors, electric current is carried both by electrons and by holes. That is, by negatively charged electrons and positively charged holes. If we consider electric current in some medium, for example, in a liquid, if a liquid is a solution of other substances, that will be called an electrolyte, and in this electrolyte the current will be carried by both positive ions and negative ions. Both positively and negatively charged particles will take part in conduction of current, in conduction of electricity. If we take such medium as a gas, sometimes an electric current may flow through a gas. For example, in a gas discharge tube or in a gas lasers. And gas discharge tubes are widely used for illumination. In a gas discharge, electric current is carried by both positive and negative particles, positive ions and negative ions and electrons. So all sorts of particles may take part in conduction of electrical current. Electrical current may be conducted, may be carried both by negatively charged particles and positively charged particles. Certainly, if positively charged particles tend to go from high potential to low potential, from positive potential to a lower potential, then negatively charged particles will be attracted to plus to positive potential. So negatively and positively charged particles always go in different directions. And that means that in semiconductor, for example, electrons will go in one direction and negatively charged particles, while holes will go in a different direction, positively charged particles. It was, by convention, it was accepted by people, by every physicist, all the physicists, that the direction of motion of positively charged particles coincides with the direction of electric current. So the electric current is always directed in the same way as the velocity of the positively charged particles in the electric current. And the motion of negatively charged particles is always opposite to the direction of electric current, because their velocity, their motion is opposite. So this convention is very useful, it's very convenient. We assume that the electric current always flows in the direction in which positively charged particles will go. That is very convenient, even in case if we have no positive particles in some medium, for example, in some metals. Even in case when there are only electrons, that is a particular case when the charges of one single sign take part in carrying the current. That is a very particular case. But even in this case, the direction of the current is assumed to be the direction of motion of positively charged particles, even if there are no positively charged particles and only the electrons take part in current conduction. So we start, on this point, we start a new topic which is an electric current. Assume we have a capacitor which was charged somehow, and this capacitor is short-circuited That is, its plates are connected by a wire, but if the wire is long enough, then it will have some resistance, and the resistance is denoted by such a rectangle on the schemes. So if the two plates of the charged conductor are connected, then there will be a current, an electric current. No matter what particles move, we may always remember that actually in most of metals, electrons will move from the negatively charged plate to the positively charged plate. But in some particular metals, the current is created by the motion of holes, positively charged particles. And so the positively charged particles will move in this direction. Well, it doesn't matter what kind of current carriers we have. We always assume that the current flows from positive to negative potential. So in this case, the current will flow and the charge will flow here from one plate to another, and this current will be sustained until the conductor has not been discharged. As there is a potential difference, then the current will flow. At the moment when the conductor is discharged and there is no potential difference and no charges on the plates, then the current will stop. It will be zero after that point in time. It means that using a charged capacitor, we can arrange a current, an electric current, but only for a short period of time. Actually, this is, as usually it's a small portion of a second, a very small portion of time when here we will have an electric current. If we want to sustain this electric current, if we wanted this current to be constant, we have somehow to sustain the potential difference between the plates of a capacitor. And in order to keep this potential difference constant, we will have to take positive charges from the lower plate and move them to the upper plate. Or we will have to take negative charges from the upper plate and move them to the lower plate. So the positive charge will be attracted to the negatively charged electrode. And so if we want to move this positive charge upward, we will have to do some work against the forces of electric field. Also, the negative charge will be attracted to the positively charged plate, and it will be repelled from the negatively charged plate, so that if we move this electric charge downward, we will have to use some force, and we will have to perform some work against the external forces of electrical field, electrostatic field. Therefore, if we want to sustain potential difference, some voltage here, we must always perform some work by transferring charges against the electric field. We must perform some work. So there must be some source of energy in order to sustain constant electric field, electric current. We must have a source of energy. Otherwise, it will be impossible. If we have no source of energy, then the electric current originates and starts flowing and very quickly decays down to zero, and the value of this current very soon will be zero. So that will be a very short time phenomenon if we don't carry the charges here between the plates, if we don't perform work. In order to perform this work, people learned to use different physical phenomena. I will just mention some of them. First of all, sometimes chemical reactions in electrolyte perform this work. The energy required to separate charges, to separate positive and negative charges, is taken from chemical reactions. In this way, chemical electrolytic cells, voltage cells, operate using chemical reaction. The other way to produce work is a mechanical work which is produced in when you move electric current, when you move a wire with electric current in a magnetic field. Then in such magnetic field, in magnetic generator, electromagnetic generator, then the work will be produced by, mechanical work will be produced by external forces. So there are several possible ways to separate these charges. Also, for example, in solar batteries, when solar energy is used, photons are absorbed from the light, from sunlight, and these photons give energy to separate the charges. So this is another possibility to separate the charges. But whatever way you choose to separate charges, you always have to produce some work, and you always must have some energy in order to sustain electric current in this circuit. So this force which acts on a current, on charges in order to separate them, the force which must be applied to positively charged particles to move them up to positive connector. This force is often called electromotive force, and it's denoted by 3 characters: electromotive force, EMF. The electromotive force is measured in volts. And volts is a unit for measurement of potential difference, and by definition, a potential difference is the amount of work which is done in carrying some charge between the points, between these 2 points, between the 2 connections, between the 2 connectors, for example, where we measure the potential difference. So electromotive force is actually an amount of energy or amount of work which is needed to carry a unit charge against the internal electrical field. And if we have such a device which uses the electromotive force, then such a device is actually denoted as a capacitor, but with different plates. So this is a battery which produces some electricity, some voltage V. Such a notation means that there is an electromotive force, an EMF, inside, whether it may be a chemical element, or it may be an electric and magnetic generator in magnetic field, or it may be some battery or anything else. It produces some voltage, and it will have some one connector which will give you a plus potential, positive potential, and another connector which will give you a negative potential. And the electric current will always flow from positive to negative, from plus to minus. And if you see such a notation on any electric scheme, in any electric circuit, you understand that this is a battery which uses an electromotive force, an EMF, which is measured in voltage. And the voltage is the potential difference on this voltage source, on this source of electric current. If we use the same battery with the same voltage, but different resistors here. Then it was experimentally established that the current, the force of electric current, will be directly proportional to the voltage applied here to the resistor and inversely proportional to the resistor. In this formula, electric current is measured in amperes, voltage is measured in volts, and the resistor is measured in ohms, and is usually denoted by a capital Greek letter omega. This is a capital Greek character omega. So 1 ampere, the force of electric current of 1 ampere equals 1 volt divided by 1 ohm, the resistance of 1 ohm. This relationship was established experimentally, and it's called the Ohm's law. Ohm's law. The Ohm's law establishes that the electric current is directly proportional to the voltage which is supplied to some resistor. In many situations, the resistor is constant, and the relationship between the electric current and electric voltage is simple. It's just inversely proportional. The current is inversely proportional, directly proportional to the voltage. But in many cases, this relationship is not so straightforward, is not so simple, and in many cases, the voltage on some element will always be equal to the current times the resistance. But in many cases, the resistance itself will be a function of electric current or voltage or temperature or intensity of light illuminating this resistor. So it may be a function of many variables. Many physical quantities may, in some situations, may affect the value of a resistor in ohms. So if the resistance depends on the applied voltage, then the electric current will not be directly proportional to voltage. This will be a non-linear dependence, and in such a non-linear dependence is actually the basis for all the modern electronics, all the modern equipment based on p-n junctions and transistors and all this sort of devices. The non-linear dependence between electric current and voltage is the basis of the modern electronics, like computers and radio communication and etc., etc. So when the resistance is constant, this is the simplest case, and this is such a situation is realized when the resistance is formed, for example, of a long wire, of a long and thin wire of small diameter, and this wire is wound on some insulating core, and then such a resistor will be constant. It will not depend on the voltage applied, and it will practically not depend on the current which flows here. But anyway, such a resistor will always depend, almost always depend on temperature. And if the resistor is heated, if there is some heat energy released in the resistor, then the resistor will change and it will depend on temperature. But this dependence is very slow. It will not immediately affect this phenomena which is observed in electrical circuit. The dependence of a resistor on temperature is the course of a slow changes in the properties of electric circuits. So, if we consider resistance of a wire, okay, I will discuss this later. Now I would like to discuss such a simple thing as connection of resistors. For example, imagine that we have two resistors, R1 and R2, connected in series. And this point is A and this point is B, and we have a potential difference, that is voltage between points A and B. And the current, which is here, flowing through this circuit, the current, according to the Ohm's law, the potential difference will be equal to the current flowing here and the total resistance of this circuit. But if we recall what is a potential difference, that this is a work which is produced when we carry a small element of electric charge through the circuit, then we will immediately understand that the total work performed when we move a small electric charge from point A to point B will be given as the sum of work done on the first part of this circuit, on the first resistor, and plus the work done when we carry the charge on the second resistor. So the total potential difference will be equal to the potential difference on the first resistor, that is the potential difference here, and the potential difference on the second resistor. Why so? Because the potential difference is defined through the work performed while an electric charge is moved. A small point electric charge is moved from point A to point B. And when we perform this work, we must first perform work on the first resistor and then on the second resistor. That's why the total potential difference equals the sum of potential differences on these two elements of the circuit. But the potential difference on the first resistor, due to the Ohm's law, can be expressed as the electric current which flows here times the first resistor, and the potential difference on the second resistor is the electric current which flows here times the resistance of the second resistor. So that this is, the electric current is the same times R1 plus R2. Why the electric current is the same in the first resistor and in the second resistor? Why it doesn't change? Why it's impossible that the current through the first resistor is 1 ampere and the current through the second resistor is 2 amperes in this circuit? It's impossible because there is a law of conservation of electric charge. And if some electric charge went through the first resistor in a unit of time, then the same charge should go through the second resistor in the same period of time. That is because we consider constant electric current. Constant electric current. Then the charge which went through the first resistor will be equal to the charge that went through the second resistor during the same period of time, if the electric current is constant. If the electric current is alternating, and if the frequency of alternation is very high, then theoretically and practically it's possible that at any given moment of time, the electric current in this element of the circuit will differ from the electric current in this element of the circuit. That may happen if the frequency of alternating current is very high, so high that the wavelengths of radio wavelengths, which corresponds to this frequency, will be of the order of magnitude equal to the dimension of this element of the circuit and this element of the circuit. So if the radio wavelength is equal to this, is comparable to this length of this element of the circuit, then electric currents here may be different and will be different, certainly. But we don't consider such high frequency signals. We don't consider alternating currents today. We consider only constant currents. For a constant current, the current through the first resistor will always be equal to the current of the second through the second resistor. That's why we can factor this current at these round brackets. Well, considering this expression and this expression, we readily obtain that the total resistor in this circuit is equal to the first resistance plus the second resistance. That is the law. That is the law for two resistors connected in series. Now, what happens if two resistors are connected in parallel? So, the first resistor and the second resistor here are two, and here is the source of voltage, which produces some voltage on its connectors. So here is the plus, and here is minus, and there will be an electric current. If two resistors are connected in parallel, as shown in this scheme, then the total electric current which flows in this wire will be divided into two parts. One part, that is electric current I1, will go here, and another part will flow through another resistor. Well, it's better to denote this current as I1, which goes through the first resistor, and the current which goes through the second resistor will be I2. Immediately from the law of conservation of electric charge, we obtain that the total electric current here will be equal to I1 plus I2. Because the total charge, electric charge, which moves along this wire will be divided into two parts. Some electrons will flow in this direction and some charges will flow in this, along this wire. But as the electric charge is conserved, it's not created from nothing and it cannot vanish into nothing. Then the electric charge which comes to this point must be equal to total electric charge which leaves this point in a unit of time. So it means that the total electric current must obey such a simple formula for this point in the circuit. The same will be true for this point or for any other point in a complicated circuit where some wires intersect and connect with one another. So in this formula we can see that the electric current, due to the Ohm's law, the total electric current, this one, must be equal to the total voltage divided by the total resistance of this circuit. At the same time, this electric current must be equal current number 1, which flows through the first resistor, and this current, according to the same Ohm's law, must be equal the potential difference between these 2 points divided by this resistance R1. And the potential difference between these 2 points is the same as here, because there is no potential difference along the wire. The potential of this conductor is the same. The potential of this conductor is the same because the resistance of this wire is assumed to be 0. That is not true. Actually, the resistance is non-zero, but it's very small. Actually, the resistance of a wire is, we choose such wires in an electrical circuits, in any electrical circuit. We choose such wiring which has a very small resistance in comparison to this resistance or this one. So it's our choice to work with such wires which have very small or negligible resistance. As this wire has negligible resistance, it means that we may assume that the resistance is 0. If the resistance is 0, it means that the potential difference between this point and this point is also 0, according to the Ohm's law, because the potential difference is the current times the resistance. And if the resistance is 0 between these 2 points, then the potential difference is 0. It means that this point and this point has the same potential, as well as this point and this point also, they have the same potential. It means that external voltage of the external battery is the same for the first resistance and for the second resistance. It means that the current through the first resistance will be the same potential difference divided by the resistance R1, plus the current through the second resistance. That will be again U, the same potential difference here between these 2 points, divided by the appropriate or the corresponding resistance. Looking at this equation, we easily understand that the same quantity U can be cancelled here, and we obtain the formula 1 divided by total resistance of the scheme is equal to 1 over R1 divided by 1 over R2. That is the formula for the resistance, to calculate the resistance of some resistors connected in parallel. So if resistors are connected in series, we have this formula. If resistors are connected in parallel, we have this formula to calculate the total resistance in this circuit. These formulas are the consequences of the Ohm's law, first of all, and the law of conservation of electric charge in a closed system. And such a circuit may be considered as a closed system because no charge is coming here from outside bodies, and no charge is lost to the outside space. Therefore, such a circuit may be considered as a closed system. Also, we assume that the wire which is used here has a negligible resistance, very small, practically equal to 0, and therefore there is no potential difference between any 2 points along the wire. All this conductor, starting from here and ending here and here, all this conductor has the same potential, electric potential. Now I have mentioned the resistance of a wire, and I would like to consider this question in greater detail. Suppose we have a wire and we have a wire consisting of 2 parts. So this is the first part, which has length L1, and this is the second part, which has length L2. If the resistance of the first part of the wire is R1 and the resistance of the second part of the wire is R2, then we will have the total resistance between these 2 points, point A and point B. The total resistance between points A and B will be equal to the sum of these 2 resistances, R1 plus R2, because these 2 resistors are connected in series, and we know the formula for the resistance of in such situations when two resistors are connected in series. Then we have just to add the resistance of the first part of the wire and the resistance of the second part of the wire, and thus we will have the resistance of all the wire. Obviously, if we have more and more sections of this wire to be taken into consideration, then we will add more and more terms here to take into account the total length of the resistance of the wire, so that the total resistance of the wire will be proportional to the length of the wire. The total resistance will be proportional to the length. The longer the wire, the larger will be its resistance. Why so? Because we know this formula, which gives you a resistance for a series, for connection in series of some elements. Now imagine a wire which has, well, for simplicity, I will put it as having a rectangular cross-section, a wire with rectangular cross-section, and the cross-section here will be S and the length will be L. And consider another wire of the same similar cross-section. So that is the same cross-section but another piece of wire. This wire will have some resistance R, and this wire will have some resistance R. And if we connect these wires in parallel, that is, if we connect this point and this point, and consider the resistance between points A and also between point B, if we connect these 2 points, then the resistance between points A and B will be calculated according to this formula for the resistances connected in parallel. But in this case, I consider the two resistances made up of wire, of pieces of wire, and the identical pieces of wire which have identical cross-section. So the total resistance will be 1 over the resistance of the first wire plus 1 over the resistance of the second wire. As they are absolutely identical, absolutely similar pieces of wire, then the resistances will be the same, and that will be equal to 2 divided by R. Therefore, the total resistance between points A, B will be equal to R divided by 2. Now, if we take these two pieces of wire and stick them together so that they form a single piece of conducting material, so that this surface will be stuck to the lower surface here. We stick together these two pieces of wire and obtain a single conducting material. The cross-section of this material will be twice the original cross-section of each wire. The cross-section will be increased by a factor of 2. And the resistance in this case, the total resistance, will be decreased by a factor of 2. Because if we take the resistance of a single wire, it's equal to R. If we take the resistance of both wires, of 2 stuck wires, then the total resistance of this piece of conductor will be the resistance between points A and B, and that will be twice as small. It will be smaller by a factor of 2. And the cross-section will be larger by a factor of 2. It means that the resistance of any such material must be, the resistance between points A and B must be inversely proportional to the area of the cross-section of this conducting material, conducting wire. The larger the cross-section, the smaller will be the resistance. And if I add more similar sections, I will obtain, using this formula, that the total resistance will become smaller and smaller. If I take 3 similar sections of wire and stick them together, the total resistance of this combined piece will be 3 times smaller than R. And if I take 2 sections, the total resistance will be 2 times smaller than R. So we may easily conclude from this formula, we may easily conclude from the formula for resistors connected in parallel, we may easily conclude that the resistance of a piece of conducting material must be, a piece of wire must be inversely proportional to the area of cross-section of this wire. Well, combining these 2 formulas from here, we may conclude that the resistance of a piece of wire must be directly proportional to the length of the piece of wire and inversely proportional to the cross-section area of the wire. And there must be some coefficient of proportionality, which is usually denoted by rho, a Greek character rho. And this coefficient of proportionality is called electric conductivity, and it characterizes the conduction properties of a material. If a material is a good conductor, then that will be a very small quantity, because good conductor will have a small resistance. But if we have a bad conductor, like an insulator, like a rubber, for example, then the resistance will be very large, and the resistance will be very large, and it means that the electric conductivity, this coefficient will be very, very large for such a piece of rubber. Actually, we often use a quantity which is inverse to this rho. Inverse to this rho. This is electric resistivity, and this one is called the conductivity, electric conductivity. So the larger the electric conductivity, the smaller will be the resistance. And the smaller the electric conductivity, the larger will be the resistance. So if we have a piece of rubber with very large resistance, because this rubber is a good insulator, then it will have a very small electric conductivity and very large rho, which will account for a large quantity of resistance. So when we have a current flowing in some medium, that is a stream of electric charges, this current can be discovered by many effects, by many phenomena which accompany the current flow in a medium. For example, if a current flows through a wire or through a simple resistor, then the resistor will be heated, because some electric energy will be released in this resistor. Heating is one of the manifestations of electrical current which flows through a resistor. Another manifestation is a magnetic field. An electric wire with a conducting wire with an electric current in it produces a magnetic field around it. We will discuss magnetic fields later, but now it's just a good place to mention that the electric current manifests itself by producing a magnetic field around the wire with the current. Another manifestation of current may be glowing and emitting light. If the temperature of the resistor increases too much, increases up to 1000 degrees or 2000 degrees Kelvin, then it will be heated to such a degree that it will glow, it will emit light as any heated body. And that is the way the electric bulb is operating when the filament in the bulb is heated to such a degree that it's glowing. It's glowing and it's illuminating the space around it, and so the electric bulb is used to illuminate the room in darkness. So in a dark so also the electric current sometimes creates chemical reactions. That is when the current goes through electrolyte. Electrolyte is, for example, a water solution of some substances, and the electric current may stimulate some chemical reactions in it. So the electric current may produce many different phenomena, many effects which can be observed. So we don't see the electric current in a wire, we don't see it, but there are many physical manifestations of electric current, starting from increasing temperature, released heat energy here in the wire, or chemical reactions, or magnetic field which is created by the wire. So there are many physical properties of electric current which can be used to measure the electric current strength. Now I would like to consider a small and simple problem. The problem is this. If we measure the resistance of a human body, for example, from one hand to another hand, between the two hands, the resistance of a human body can be measured to be about 22 kilo ohms, 22,000 ohms. And the question is, assuming that resistance of human body is equal to this given quantity, find the current passing through a person who touches a 220 volts cable. So there is a cable under 220 volts. Well, volts is a unit of measurement, and that will, the voltage should be better. We should better use a different character like U, like character U, to denote the voltage. And the voltage is 220 volts, as in usual electric circuit used for illumination. So we have a wire under such a voltage, 220 volts and 50 hertz. In Russia we have 50 hertz. That is 50 times the alternating current, alternating voltage is changing direction 50 times per second. That is an industrial current, industrial voltage. And a human being having such a resistance of human body touches such a cable which is under such voltage. We have to find the current which will flow through the body of that unfortunate man, an unfortunate person. So using the Ohm's law, we can immediately obtain that the current will be equal to the voltage divided by the resistance of the body. And the voltage is 220 volts, and the resistance is 22 kilovolts, which means 22 kilo ohms, which is 22,000 ohms. So 220 divided by 22 will be just 10, and 1 divided by 1000, that will be 10 volts. Okay, let's do it this way: 10 volts divided by 1000 ohms. If we have 1 volt divided by 1 ohm, that will give us 1 ampere. If we have 1000 ohms, then the current will be 1000 times smaller. That will be 1 milliampere. That is 1000th part of an ampere. So here we will have 10 milliamperes. Milli means 10 to the power of minus 3 amperes. That is what we call milliampere. A milliampere is a 1000th part of an ampere. So the electric current which will flow through a body of this person will be equal to 10 milliamperes. Is it a large current? At first glance it seems to be small, well, just some milliamperes, but I would like to tell you that the current of 50 milliamperes, just 5 times that value, is practically fatal, will have fatal consequences, because a human heart will not operate if a current of 50 milliamperes flows through the human body. Actually, a human heart or heart muscle will not operate properly, and the current, just 5 times that value, will be a deadly current. It will have fatal effect. So this is very dangerous. This is very dangerous. And it should be mentioned here that the action of a current on a human being depends on the state of health of human being. If a person is young and healthy, he may well tolerate such a current. It will be very unpleasant, but no bad consequences for one's health, no immediate consequences will be observable. But if a person is after illness, if he was sick, if he is weak, if the state of his health is very low, then such a current may have very dangerous effect on person's health, very dangerous. And if we increase this current by just a few, by a factor of 5, it may be deadly, it may have fatal effect. So also I should tell you that the resistance of human body is a very approximate figure. I have taken here 22 kilo ohms so that it will cancel here. But actually it may be a little bit more, it may be 25 kilo ohms, it may be 30 kilo ohms, but it may be even less than 22 kilo ohms. Sometimes the resistance of human body depends on many factors, such as the temperature of the air around us, the humidity of the air, and the state of health of a person. If the state of health, if his mood is low, if he had a bad night, not slept well at night, then the resistance of his body will be lower. And if he was sick yesterday, the resistance will be lower. And then the current will be higher, because the resistance is in denominator. The smaller the resistance, the larger the current. So the actual amount of value of the current which will flow through the body will depend on the state of health of this person. And that is varying thing, and on the temperature and humidity of surrounding atmosphere. So it's a varying factor, and sometimes a person touches 220 volts and says, oh, nothing, well, I can easily tolerate it, nothing at all happened to me. But next time the situation may be different, the humidity in the atmosphere may be different, and the resistance will be different. It may be small, it may be half that value, and the current which flows through the body will be twice or more than that value, and that may be very, very dangerous. So I have considered this problem in order to discuss this fact that the electric current is dangerous for a person, and what kills is not the voltage, it's the current that kills a person. It's the current, not the voltage. Well, and the last thing I would like to discuss today is the heating of resistors when the electric current flows through a resistor R. Then, according to the Ohm's law, the potential difference here on this resistor, the potential difference will be equal to R times current I, which flows here. And we recall that the potential difference is just a work which is performed to carry a small amount of charge delta Q through this section of the circuit. So that the work performed can be written as Ri delta Q. And also we may recall that the current, by definition, is the charge which flows here per some time period during which the charge delta Q has flown through the cross-section of this wire. This is actually the definition of what the electric current is. The electric current is the amount of charge which flows here divided by the time period during which this charge crossed certain point in this wire. So using this definition of electric current, we may substitute electric charge from this formula and obtain that this is electric charge is electric current. We will obtain I squared times delta T. And the work performed during time delta T may easily give you a quantity which is called a power. Well, it may be denoted by letter P, which is the work performed in some time period delta T. If we divide by delta T this formula, we will obtain the power, the electric power, that will be Ri squared. So if we have an electric current I flowing through the resistor R, then this power will be released on this resistor. Where does this power, or where does this energy go? The power is the energy per unit time. Where does this energy go? It goes into heating the resistor, into increasing its temperature. Using the Ohm's law, which connects the current, the resistance, and the voltage, we may modify this formula to show in this way, to be put in this way, like voltage times current. Also by using a voltage as also using resistor as voltage divided by a potential difference divided by current. We may rewrite this formula substituting for resistor this formula U divided by we will obtain the same thing, certainly. Or substituting electric current from here as U divided by R, we will obtain U squared divided by R. So all these are very good formulas to calculate the power, electric power released on a resistor if we know the resistance and the magnitude of electric current, then we can easily calculate using these formulas the electric power which is released here, and this electric power is usually turned into heat power. This electric power, this energy goes to heat it, to increase the temperature of this resistor. So that's a very important issue, that any electric circuit element has its own resistance, and then there is some heat energy released on any element of electric circuit. For example, if you have an electric bulb of the power of 100 watts. Electric bulb of 100 watts. Then, if this bulb is connected to the external voltage of 220 volts, then we can easily calculate what electric current will be flowing through this electric bulb. That will be the power of the bulb divided by voltage, and that will be 100 watts in SI system divided by 220 volts, and that will give you in amperes approximately 0.5 amperes. Approximately half an ampere will go through this bulb so that it can produce such a power of illumination 100 watts. Actually, if you take some electric appliance like a vacuum cleaner, the power of a vacuum cleaner may be 10 times this quantity, maybe up to 1000 watts. And then the electric current taken by this vacuum cleaner will be 10 times larger, will be 5 amperes. So a vacuum cleaner, not very powerful, but ordinary vacuum cleaner of 1000 watts electric power will take the current of 5 amperes if you attach this, if you connect this vacuum cleaner to 220 volts. So that is the relationship between the electric current and the supplied voltage and the power released in this element. Okay, on this point, let us finish this lecture. Next time we will solve more problems on electric current. Now, goodbye, everybody.